Humans. Today we are going to be talking about patterns. We're going to look at if the pattern is increasing or decreasing and if it represents a linear or an exponential pattern. So we've been talking about lines a lot, so you should kind of recognize what we're looking for when we're talking about lines, but we're also going to introduce this new type of function called an exponential function. So we're going to look at what these patterns look like. We're really just focusing on patterns this week. Okay. So first thing, what does increasing mean? Well, increasing in math, first of all, you're going to read the function from left to right. So always reading from left to right, just like you read a book. So you're going to look at the graph and look at it as it moves from left to right. What are the y values doing? So if the y values are getting larger and larger and larger, the function is increasing. However, if you read the function from left to right and the y values are getting smaller, then it is a decreasing function. So what we're talking about, the word increasing and decreasing, is referring to our y values. What are our y values doing as we look from left to right? So as our x values are increasing, right? That's what left to right is. Our x values are getting bigger. What are our y values doing? So in a linear function, we're going to have a constant rate of change, right? Our slope, rise over run. Remember, we drew those slope triangles. It doesn't matter where you draw them. They all simplify to the same slope because it has a constant rate of change. But this new type of function we're going to talk about, exponential functions, they don't have a constant rate of change. They rapidly increase or rapidly decrease over time. So instead of growing constantly at a consistent rate, you earn $7 a week for your chores or something. Instead, now you're talking about earning more than that. So maybe you invest your $7 and you earn a bunch of interest and it grows faster. That's exponential. So we're talking about things that can grow faster or slower over time. So not a constant rate of change, different than our linear functions. All right, so we're going to look at these patterns and see what they mean. We want to know, are they increasing or decreasing? Okay, that's what we're going to start with first. So are these functions increasing or decreasing? And then we're going to look at how that's happening. Okay, so first thing I always want to do when I'm given a table is look at how do I get from my first given y value to my second given y value. This looks like a change in plus 10. And then I also want to look at my x's and see how do I change from my first x point to my second x point, and this is a plus 1. Now, if we knew this were a linear function, that would be all we need to do because we know it's going to have a constant rate of change. So that ratio of 10 to 1 will stay the same every single time. However, if this were exponential, maybe the next time we don't go up by 10, we go up by 20 or something. So we want to look at least 2 points now that we don't know if it's linear or exponential or something else, right? So we want to look at least 2 points. So instead of stopping right there after I've investigated this one, I also want to look at the next one. Oops, here we go. All right, so I also want to look at the distance between 39 and 49. That also looks like plus 10. And then between 3 and 4 is also plus 1. This is appearing to be a constant rate of change. So again, plus 10, plus 10, plus 1, plus 1. So this is a constant rate of change. So I'm thinking linear, but that's not really what I'm asked here. I'm asked if this is increasing or decreasing. Well, on the left of my table, my x values are increasing. So that's reading from left to right. And as my x values increase, my y values are also getting bigger by 10, right? We're adding 10 each time. So this one is increasing. Okay, so it's changing by a constant rate. So I'm thinking this is linear. This is just a preview of things to come, right? And it's increasing because the values are getting larger as my x values get bigger. Again, left to right. So we have to be looking as our x values increase as well. All right, give this next one a try. See what you think the pattern is. Okay, so we know to go from 2 to 3, I could add 4, right? And then from -1 to 0, I could add 1. Let's see again if that pattern continues, because if it's a constant rate of change, it will. If it's not a constant rate of change, something new will happen. All right, so when I go from here, 6 to 18 is definitely not plus 4. So that's not the pattern. because even our exponentials, they do change over time, right? They grow more rapidly over time, but they still have a pattern, a very specific pattern. So we need to try and find that pattern. The difference between a linear function and an exponential function is that exponential functions are going to grow by multiplication. They're going to get faster over time. So when we multiply, the bigger the number we multiply by, the faster things grow, right? So instead of adding a constant rate of change like our linear functions do, now we're going to be multiplying. So let's see if instead of finding what we would add to get from 2 to 3, what would I multiply by to get from 2 to 3? So if I wanted to get from 2 to 3 by multiplying, I'd multiply by 3. And in fact, I'm going to not use a x to do that. We're going to use a little dot times 3 to indicate multiply by 3, right? All right, let's see if that pattern repeats. So to get from 6 to 18, that's also multiply by 3. Sweet. So now I'm seeing a pattern here. That's what we're going for. Remember, we're looking for patterns. So either we're looking for an addition pattern or a multiplication pattern, or it could be something totally different, right? Who knows? Okay, and then to get from 18 to 54, again, we're multiplying by 3. Over here, this is increasing by plus 1, plus 1, plus 1. This is not a constant rate of change, so this is not a rise over run situation. The reason I looked at my x values is just to make sure, are they increasing? Am I looking at this function from left to right in my table? And indeed I am, because I'm getting bigger over time. So what are my y values doing? They're also getting bigger over time, even more rapidly than my last function, right? So this is increasing, but not by a constant rate of change. So this one's actually exponential. But again, we're going to keep exploring that as we go forward. All right, you look at this next one, see what you get. Or I'm going to look at this one with you, but then, try it yourself too. Okay, now we go from 4 to 2. So either I could be subtracting 2, but I also want to consider the multiplication option. I could multiply by 1/2. Okay, so when we think about multiplication, if the numbers are getting smaller, we're multiplying by a fraction, right? So, or you can think about it as division. If what you think is like, oh, to get from 4 to 2, I would divide by 2. Remember, dividing by 2 is equal to multiplying. Again, I don't love that x term, or x as my multiplier there, but we're multiplying by 1/2. So again, dividing by 2 is equivalent to multiplying by 1/2. Okay, so either I'm subtracting 2 over here, but that doesn't work when I go from 2 to 1. So I'm not subtracting. So this must be multiplication by 1/2. Let's see if that works. If I multiply 4 by 1/2, cut 4 in half, we get 2. That works. If I multiply 2 by 1/2, cut 2 in half, we get 1. Ding. So this is exponential. Again, because I'm multiplying to get to each new value. And then my x values are increasing. I'm going from 0 to 1 to 2 to 3 to 4, right? So my x values are increasing, but my y values are getting smaller, right? They're getting smaller and smaller. 1 is smaller than 2, 1/2 is smaller than 1, and so on and so forth. So this is decreasing. Our y values are decreasing over time. All right. Also, I kind of want to just give you a little visual of these. If we were to think about what this would graph like, we'd get something like this, right? If you think about reading this function from left to right, if you were to jump on that line and take a hike, that's a hike, right? That's a positive slope. Positive slopes are increasing over time. If you think about this one here, if you were to graph this, you would get something that looks like this, okay? It's growing rapidly over time. It's curved because it's increasing rapidly over time. This one is decreasing. It looks like that, right? It's decreasing, but more rapidly than a line, which would be a constant rate of change. All right, give this you-try problem a shot. So to get from 33 to 11, we would subtract 22. Or we could divide by 3, right? So either we're dividing by 3, which is the same as multiplying by 1/2, or we're subtracting 22. So let's look at that. And then to go from 11 to negative 22, that would be different. That would be subtracting, 33? No. Yeah, 33. Yeah, so these are going by different values because look, we went from -3 to -1, that's +2. And then we went from -1 to 2, that's +3. So this pattern, be really careful looking at your x values too, because this does have a constant rate of change, but my x values went by different amounts. So pay attention to that. So when we look down here though, to go from 45 to or -45 to -55, we'd subtract 11, right? And when we went by 2 here, this is a change in 1. We went from 4 to 5. When we increased by 2 up here, we did 2 times 11, 22. So this does have a constant rate of change. If I wanted to fill in the values, we could do from -3 to -2. So this went from 33, and then we'd subtract 11. This would be 22. And then when we get to -1, we have 11. If we wanted to do 0, we'd get to 0. And then 1 would give us -11, right? So I'm just filling in the gaps of this table over here to show you that this does have a constant rate of change, but it's subtracting, right? We're getting smaller and smaller and smaller as our x values get bigger and bigger and bigger. So this is decreasing, and it's linear because it's decreasing by a constant amount each time. All right. So now we're really going to focus just, is it exponential or linear? So look at these, see if you can piece together. I know it says example and you try, but see if you can figure this out based on what I kind of previewed already. All right, so again, we're going to look, how would I get from 2 to 6? Either I could add 4 or I could multiply by 3, so I need to check the next one. Clearly, to get from 6 to 18, I would multiply. So because this is a multiplication pattern, or a geometric pattern, if you remember back to when we talked about our geometric patterns, right? So this is changing by multiplication by 3. So we're multiplying by 3. So this is exponential. And again, it's going to grow like this over time. We are going to have a curved line here. All right, how about this one? Well, I'm adding 10. Looks like I'm still adding 10. Still adding 10. So this is linear because it's a plus 10. So when we're adding or subtracting, we're linear. So if the pattern is multiplication, then it's exponential. If the pattern is addition, then it's linear. Okay, so it's constant. When we are adding the same amount each and every time, that's a constant rate of change. That's the definition of a line. Okay. Here, this is that same one we talked about before. So this pattern changes a little bit because we have missing values over here, but this is linear because I'm subtracting 11 each time. So again, addition and subtraction are basically you're adding a negative is the same as subtraction, right? So you can think of it as addition every time if you want, but in this case, we're adding a negative value. So again, that's why this one was decreasing. This, however, is multiplication. We are multiplying by 1/2. If you are multiplying, that must be exponential. All right, so this one is getting smaller over time, but it's exponential because the pattern is changing by multiplication. All right, so when we look at a graph to determine what's happening, it's really straightforward. If it's a straight line, it's linear, right? Meaning it has a constant rate of change. If it curves, then we're talking exponential, right? So we're just looking, do we have a straight line, a constant rate of change? Every single distance between the points is a constant ratio, right? Or does the distance between the points change over time and therefore give us a curve? So when we look at this, and we're also looking increasing, decreasing, right? So as we read the graph left to right, what are my y values doing? So in this case, as I read my graph from left to right, what are my y values doing? They're getting smaller and smaller and smaller by a constant rate. So notice if I were to draw a slope triangle in here, where's a nice pretty whole number? Let's actually just go between these points here, whoop, whoop, right? And then here, all these slope triangles would be equivalent. The distance between these points would be the same, right? Or if I did a big slope triangle and I simplified it down, it would simplify down to the same. So this is decreasing Again, because as I read from left to right, my y values are getting smaller. If you were to jump on this line, you would slide down, decreasing, and it is linear because it has a constant rate of change or a slope, right? All right, let's look at this one. Well, here looks like the distance between these two, I go over one, up one. That would be okay, good. But in the next one, I go over one, up two. So notice over one, up one, but now I go over one, up two. And the next time I'm gonna go over one, up, up four. See how that's getting bigger each time? This is exponential growth. This is what you want your money to do, right? You want to put it in the bank or in some kind of investment and have it grow really, really fast. That'd be ideal, right? So then the next year, ooh, yeah, now you're talking, right? Okay, so this is getting faster and faster over time. We get more and more growth between each. If you think about the X values as years or something, you're getting more and more money each year. That's exponential growth. Okay, so this one is exponential. And as I read this function from left to right, what are my y values doing? They're going up and up and up. So this is increasing. Again, as I read this function from left to right, my y values are increasing. All right, let's look at this next one. Okay, I see a curve, so I'm thinking exponential because the distance between this point and this point is not the same as the distance between this one and that one, right? So this height is bigger than that height, meaning that this does not have a constant rate of change. Also, it's curved, so it's exponential. Now, as I read this function from left to right, what are my y values doing? Well, they're getting smaller, right? They're getting closer and closer to zero here. So they are decreasing. This is the opposite of what you want your money to do. You don't want to invest it and have it lose all the way down until you have nothing left, right? That would be a bummer for you. Okay, so over here you have another function. Let's read it from left to right. So if I were to draw a little slope triangle here between clear points, and then maybe, let's see if we can find another one. But this is changing by a constant rate of change, right? All of these are going to be equivalent slope triangles here. If we were to simplify them down, they're not pretty whole numbers because this graph doesn't touch a bunch of whole numbers, but this has a constant rate of change. If I go over one, I'm going to go up by the same amount each and every time. It's linear. So it looks like a line, right? So it's linear. And as I read from left to right, my y values are increasing. This is a hike. You jump on this line, you're going to take a hike. This is a positive slope, also known as increasing. Okay. All right. So how could we create a linear or an exponential table? So we want to do this to represent growth or decay, and a table that represents, okay. So yeah, don't worry, I got you. Okay, here we go. So a linear function, what's the key here? What's the most important part of a linear function? Constant rate of change, right? So it doesn't matter where you start. You can start at 0. Make your life easy. You start at 0, 0. Let's say our slope is 1. Again, keep our life easy, right? Let's say our slope is 1. Well, that means as x goes up by 1, y goes up by 1. 2, 2, 3, 3. That's a linear function because it has a constant rate of change. Now, you could come up with infinite linear functions, right? You can go up by 5 each time. You can go up by 1/2 each time. Literally infinite options. You can start at -10 and 2. Right? And then maybe I'm going to increase by 3. So I'm going to add 3 each time. So this is going to take me to 5 plus 3, 8 plus 3, 11. And my x's, maybe I only go up by 1. -9, -8, -7. Again, as long as you are adding a constant rate of change each time, the change in the y's divided by the change in the x is exactly the same between every single point. That is a linear function. Now, in this case, both of these were increasing, right? Because the x values are increasing and so are the y values. If you wanted to change that and make one of them decreasing, you could drop some negatives in front of this, and now this one is decreasing, right? Negatively sloped because we are going to get bigger in our x values, but smaller in our y values. All right, exponential, what's the key here? Now we're multiplying to create our pattern. So now let's start with, 0, 1, okay? So because we're multiplying, we're not gonna have a y output of 0 because you can't, well, we'll get into that later. But start with an actual y value so that you can multiply easily. Let's multiply by, let's multiply by 5 because I like 5. So 1 times 5 is gonna get me to 5. And this would be, again, increasing by maybe ones over here. I don't know what's going on with my hair today. Sorry, guys. Okay, so we multiplied by 5. So then our next one, now I have to take 5 times 5 to get to this point over here, which would give me 25. And erase that just so it's not confusing where it came from. Again, we are multiplying each output by 5 every time, multiplying by 5 to get to our new values. So we're going to do 25 times 5, which is 125, would be my third value. Notice this is increasing dramatically. So 1 to 5, it's a 4 apart, right? And then 5 to 25, that's a much bigger distance between those 2 points. Exponential growth. Now, and we call it growth when we're increasing, we call it decay when we're decreasing, okay? So this would be exponential growth. This one was after I changed to negatives. This is decreasing over time. So this is growth, also known as increasing. All right, what if we wanted to do one that decreased? Again, you can try anything you want here as long as you're multiplying to get to your next value, it's exponential. But I'm gonna show you a decreasing option just so you can see what that looks like. So what if we started at 0 and 125? I'm using this table to the left to show you what's gonna happen here. Okay, and then we go to 1. Now we're gonna multiply, stop using an X for now. Now we're gonna multiply by 1/5. Okay, so now it's like dividing by 5, right? So each value will decrease rapidly. So 125 is going to become 25 when I multiply by 1/5. And then I'm going to multiply 25 by 1/5 again, which will get me to 5. And then I'm going to multiply by 1/5 again, which will get me to 1, and so on and so forth. So these values are decreasing. So we call this decay when we're talking about exponential. You can also say decreasing, right? As we read this function from left to right, my y values are getting smaller and smaller and smaller. So that's what I want you to be thinking about this week. Basically, we're looking at the difference between multiplying to get to our next value and adding to get to our next value. So again, when we're adding, it's a constant rate of change. If you're multiplying, the value that changes each time will get bigger and bigger and bigger, or smaller and smaller and smaller, depending on what you're multiplying by. So that's patterns we're looking at this week. Hopefully that makes sense. Have a wonderful rest of your day. Okay, one more important point I want to make. When we're talking about geometric sequences, that pairs with exponential functions. So hopefully that's a review of stuff we talked about first trimester, but on your Delta Math assignment, it does bring that concept back. So remember, an exponential function is going to an exponential function is also represents a geometric sequence, which has a common ratio. That's the value that we multiply by each time, whether it's a fraction or a whole number. And then a arithmetic sequence is going to be a linear function, right? We're going to have a constant rate of change, which they call a common difference. So your slope value is your common difference, what we're going to add or subtract each time. So when you're looking at those sequences, basically we're removing the x part of our table. We're just looking at what the y values are doing. And I want you to tell me, is it arithmetic, which is going to pair with linear? And what would the common difference be, the value we add or subtract each time? And then is it geometric, which pairs with exponential? And what value are we multiplying by each time? So that's in your Delta Math this week.